In this segment, we are going to look at the first of Newton's 3 laws of motion, and we will take a brief look at 6 interesting ideas of physics associated with the first law: inertia, velocity, centrifugal feeling, centripetal force, friction, and weightlessness. We just looked at Newton's law of universal gravitation, that all objects have mass and come preloaded with their own gravitational field. All things naturally pull toward one another. The greater the mass, the greater the tug. So if they are pulling toward each other, why don't the moon and the earth crash into each other? Well, they would if gravity was the only issue to consider, but they also have their forward motion, their forward inertia given at the creation. In Newton's Principia, he not only described his universal law of gravity, but he also described 3 laws of motion. And to help us remember these laws, we have a train with the 3 laws simplified and illustrated on each car. Law number 1. Objects at rest will stay at rest unless acted on by another force. Illustrated by our sleeping dog at rest, about to be acted on by another force, our happy little cat. Law 2. F equals ma. Force equals mass times acceleration. And we've illustrated this formula on a chalkboard with 2 massive knights forcefully accelerating toward each other. And the third law: for every action there is an equal and opposite reaction. Illustrated by our young man slipping off of his skateboard. The skateboard goes off in one action, and he goes off in an opposite reaction. Now, it's easy to confuse these 3 laws of motion with the 3 laws of thermodynamics, which we looked at in the heat segment, because there are 3 of them. The 3 laws of thermodynamics deal with the physics of how heat moves, and the 3 laws of motion deal with the physics of how things move. An important part of science is the ability to predict, like predict the motion and movement of planets and objects. But what causes things to move in the first place? What causes something to speed up or slow down? The answer is force. Only a force can cause something to move, and not surprisingly, Aristotle and Newton had different views on how force affects objects. Look, when the fan turns off, the motor slows down and stops. But why does it stop? Aristotle, and probably most of us, naturally believe it's because no more force is being applied to it, so it grinds to a halt. That's how we think of motion. Forces keep prodding things along, and as soon as you stop prodding them, they naturally slow down and stop because the force is off of them and no longer giving them motion. When you see films of crash test dummies in cars, it tends to reinforce our normal thinking of the laws of motion. The car is in motion, and a force, the wall, stops the car, and the windshield and the steering wheel stops the dummies. Then all is at rest. But Isaac Newton said something altogether different in his first law of motion. Aristotle said that objects in motion tend to slow down and go to rest. Newton said, no, that is not the way the planets or anything else really behaves. In fact, it's just the opposite. Objects in motion tend to stay in motion. That is Newton's first law of motion. Although Galileo said nearly the same thing 50 years before, it was Newton who built on Galileo and framed the ideas of motion into scientific, coherent laws. Newton realized that objects have no force in themselves to change their motion. It takes an outside force to make a mass change motion. Otherwise, objects have no internal reason to change what they are doing. Things come into being or change only because of an outside influence. This was his first law of motion, and like the rest of the Principia, it was written in Latin, and it looked like this. But in plain English, it says, Law 1. Every body continues in its state of rest, or in a constant motion in a straight line, unless it is compelled to change its current state by forces impressed upon them. Or in even more plain English, objects at rest tend to stay at rest, and objects in motion tend to stay in motion unless a force acts on them. Now, this is hugely counterintuitive to how we see everyday life, because the forces that actually act on us, like gravity and the electromagnetic forces of friction and even air resistance, are so much a part of our everyday life, we never give them a second thought. Newton said the reason the book stops on the table and the reason the arrow falls back to earth is not due to a natural state of rest or that it runs out of motion. No, the reason they stop is because forces are actively acting on them to stop their normal motion. If Newton had known about cars, he would say that the car normally wants to continue in a straight path without you adding any extra energy or stepping on the gas pedal, and it will continue forever unless other forces act on it. And when Newton said other forces, he was not primarily thinking of crashing into a wall or another car. He was saying that the book stops because forces of physics, like gravity and friction, stop them. Because the very fact that we are living on a planet means that there are always forces acting on us to slow our motion. We don't need a wall or another car to crash in us to stop us. Gravity is always a force on a planet, pulling you down toward the center, stopping your motion. Friction is another type of force that slows your motion. This disk is often used to demonstrate low friction forces. It looks like it should be pronounced Euler, but this German name is pronounced Euler. It works by spinning a heavy smooth disk on a very smooth surface. This first law of Newton's is often called the law of inertia. Inertia is what these massive asteroids are displaying. Assuming that they are far away from strong gravitational attraction, like planets or stars, they will lazily remain unchanged in their motion. Of course, each asteroid has a small gravitational attraction, and eventually these asteroids will group together and travel as a group, maybe until the end of the universe. Inertia comes from the Latin word meaning laziness. Inertia is what you have in bed when the alarm clock goes off. You resist change in your motion. You are inert, and you want to stay that way. On the other hand, when you are in motion, playing outside at night in the summertime with your cousins or your brothers and sisters or your friends, and your parents announce that it's time to go home, you have great inertia to continue doing what you are doing. You resist the force to rest. After all, you were just starting to have the most fun of the whole night. You resist changing. So inertia, laziness, works both ways. Things want to remain at rest, or things want to remain in motion. Think of the word inert. Argon is an inert gas, meaning it is too lazy to combine with anything. In fact, argon is the Greek word for lazy, and inertia is the Latin word for lazy, and lazy is the English word for lazy. So a technical definition of lazy inertia is that inertia is the resistance an object has to change what it is currently doing. That's why it is more difficult to get your bicycle going to begin with. You must overcome the bicycle's inertia, the laziness of wanting to stay at rest. But once you get it going, it's easier to keep it going. Notice inertia is not an external force. It is not how fast you are going. It is the natural resistance every object has in changing what it is currently doing. You can imagine that the heavier you are, the more massive an object is, the greater the resistance it will have to change. Here is a marble, and here is a rock. Which one will resist change most? Well, the rock, because it has way more mass, it is way heavier, and thus it has much more lazy inertia. This is Newton's first law of motion, illustrated in Train Car 1 by our resting dog, who will stay at rest until acted upon by our energetic little cat. What about velocity? That's another word we hear about but don't really understand well. What is velocity? Now, when you say the word speed, you get that because you use the word every day. You even associate it with this thing here. It's even called a speedometer, a speedometer. A meter for speed. It's a little scale with a pointer telling you how fast you're going. It also has a little meter telling you how far you went as well. After all, what is speed but driving somewhere and getting there on time? The only way you can cover the distance you want in the time that you have is to go a certain speed. This scale is useful, but it's actually pretty limited. It's very similar to the scale in your bathroom. There's a little dial, and it moves, and it tells you one thing. This tells you your weight. This one scales speed. This one scales weight. This one scales temperature. All of these scales tell us how much, or the magnitude. How much do I weigh? How much speed? How much heat? If a scale measures something simple like this, physicists call it a scaled quantity or a scalar quantity, the amount of stuff measured by a scale. So, to be really useful, your scaled weight needs to be combined with some kind of direction, weight lost or weight gained. Now, that is very useful. When you add essential directional information to your scaled-off number, this combined information, this useful information, is called a vector. Oddly enough, a vector is also the name of a disease-carrying animal like a rat or a tick, which we will get to in a minute. A scalar is one piece of information. A vector is at least two pieces of information, including direction. So if a vector is some animal carrying a disease like a rat or a flea, why in the world would they choose that word to describe this physics idea? Actually, it's not that bad of a choice. The word vector comes from the Latin veho, meaning a carrier, or someone who carries something in a direction. So a rat vector carries fleas, and from there, the flea vector carries microorganisms causing disease. So physicists got a hold of this idea, this carrier idea, and they said, hey, that is just what we need. We need a word that describes how something gets carried along with our scalar number and adds information. How about vector? So velocity is speed carrying direction along with it. You can see now why speed and velocity are often confused, because speed is a part of velocity. Speed plus direction. Say that you are going 55 miles an hour in a straight line. Your speed and your direction never change. Your velocity is the same. But as soon as you turn that steering wheel just a little bit, you change one of those vectors. You change your direction, and thus you have changed your velocity. Two cars are each going the same speed as they pass each other, 55 miles an hour. The same speed, but they are going in different directions, and thus they have different velocities. You can think about this next time you drive in your car, because this change in either direction or speed can really matter to some people. Like to who? Like to you and me driving around in our car every day? Not really, because what matters to us is speed and distance. The fact that velocity is speed plus direction really is not that significant to us because we have a road that we travel on right underneath us. But if you're an astronaut zooming around at 17,000 miles an hour, that's 5 miles a second. The fact that your direction could be off or on could make or break your day. So you and I do not use velocity on a regular basis, but pilots do, and so do those who plot the paths of planets and space stations. They use these vector quantities all the time. Next, centrifugal feeling. Notice we did not say centrifugal force. What is centrifugal feeling? It's the feeling you experience when a car turns a corner, changing its velocity, and you feel the door press against your body. It's that feeling that pastes you against the wall on various amusement park rides. Centrifugal means fleeing away from the center, because that's what feels like is happening. A force is pushing you away from the center. But in this universe, no such pushing force actually exists. We sometimes call these false forces or fictitious forces. A false force is when you feel like a force is acting on you, but it's a misinterpretation of real forces. Real forces require actual forces in physics acting on real objects. Centrifugal force is a mental misinterpretation of Newton's first law of motion. This tetherball animation helps to illustrate it. The tetherball is going in a circle because a string is attached between the ball and the pole. You hit the ball, and the ball continues in a circle. You might think that centrifugal feeling is pushing the ball away from the pole. After all, that's what centrifugal means, pushing away from the center. But there is no force that actually pushes the ball away from that pole, unless you had magnets in the pole or magnets in the ball, but we don't have magnets. But we do have Newton's first law of motion, and it says this ball wants to continue going in a straight line. But the electromagnetic forces holding the string together and holding the string to the ball force it in a new direction, constantly changing direction, even though the ball wants to go straight. It is sometimes pronounced centrifugal, so that's how we will pronounce it here at the end, just so you get used to it both ways. Here's a yo-yo. It is very similar to a tetherball because it too is attached by a cord. Now, if centrifugal feeling was a real pushing force fleeing away from the center, then when I cut this yo-yo string, it should move radially away from my hand, like sunbeams radially going away from the center of the sun. But it won't. It will fly away at a right angle from the center. Newton says this is because it is going in the direction that it wants to keep going, in a straight line. Centrifugal feeling is a useful way to describe what is happening from the object's point of view. It even makes some mathematics easier by assuming it to be a real force. But it's good physics to remember that centrifugal feeling is not a real physics force. There is another force that you may have heard of called centripetal force. The word centripetal means center-seeking, the direct opposite of centrifugal. Centrifugal means center-fleeing. You can kind of remember this because centra means center, and petal, well, it means seeking. But it is spelled just like our English word petal, which are the leaves surrounding the center of a flower. When you see a flower, the petals are center attached, center seeking. They are centripetal. Centripetal force is defined as any force that keeps something going in a circular motion or in a curved path. Centripetal force is also not a fundamental force, but rather the name serves as a sort of placeholder to describe forces or a combination of forces that pull an object toward the center of a circular path. Here, the centripetal force is the force attaching the string from the ball to the pole. Centripetal force is the word that we use to describe any force needed to keep an object following a curved path. In the case of this yo-yo, my hand and the yo-yo are connected mechanically by this string. My hand is constantly pulling on this string, providing a mechanical connection to the yo-yo, constantly pulling it out of its desired path to go straight, pulling it in toward the center, toward my hand, pulling it centripetally, constantly changing its velocity because it is constantly changing its direction. Satellites have a centripetal force on them as they go around the Earth, but the source isn't mechanical like the string on the yo-yo. It's gravitational. Gravity is providing an invisible centripetal force that pulls satellites toward the center of the Earth. And finally, when your car goes around a corner, it is actually following a circular path. But what is causing this centripetal feeling, this center pulling or center seeking action? It is another secondary force caused by the combination of gravity and electromagnetic forces, and we call this particular secondary force friction. The car, or anything else in motion, is actually always going in a straight line at any particular moment in time, but other forces act on it to divert the straight motion. In this case, your turning the wheel exerts a force on it from the friction between the tires and the road. And what exactly is friction? First, you need to understand that friction is really not that well understood or that well defined, and that goes for a lot of physics today. So there's a lot of frontier to explore in the future. A lot of time and money is spent trying to overcome this force. But here's some of what we think we know. Friction is not a fundamental force, as we spoke of, like the electromagnetic, nuclear, or gravity forces. At very least, it is part of the electromagnetic forces that we talked about earlier. When two surfaces are in contact, the electro and magnetic interactions of their surfaces produces heat and it resists motion. But what is really happening if we zoom in at nearly the atomic level? Here, friction is literally surface roughness. What looks like a super smooth surface to our eyes at the molecule level is actually like rough mountain ranges. And when two surfaces are in contact with each other, they rub on each other. And the peaks will run into each other and hinder the motion of the mountain ranges as they try to pass by. If the peaks are really rough, they grind together. And we call that grinding friction. If you have no friction, Newton's first law just takes over and things keep moving through inertia. Without this sticky interaction, you could never pick up this glass or a pencil. You couldn't drive a car on the road. You couldn't even walk on the street. So we need friction. But we also spend a lot of time and money in industry and in our machines trying to overcome this force. So things in motion remain in motion. We see this particularly in space, and this of course applies to things like the space station. The space station itself is pulled in by gravity. But then, why aren't the astronauts in the space station also affected by gravity? Why aren't they pulled down? Why do they seem to free float in zero gravity? In reality, astronauts are not free floating in the space station. They are very much affected by gravity. In fact, astronauts weigh a full 90% of what they normally weigh on the Earth's surface. So a 150-pound astronaut weighs 135 pounds in the space station. That's hardly weightless. What you see in movies of people seeming to float around the space station is actually people and space station zooming over the Earth about 17,000 miles an hour at the same time that gravity is causing them to fall toward the surface. After all, the space station weighs over 1 million pounds, and gravity is pulling hard on all that mass. When first put into orbit, rockets propelled the space station forward to 17,000 miles an hour. And even at 200 miles above the ground, there is still a small amount of air drag that slows the space station down a tiny bit. This is a force in Newton's first law, acting on the inertia of the massive space station to slow it down. That's why there is a rocket attached to the space station to occasionally give it a boost to maintain the needed orbital speed and distance from the ground. Look, here's our little man, and he has just jumped out of a high airplane. He's falling fast and getting lots of air resistance. Now, as he is falling, let's put him inside of a box, so the box will take all of the air resistance. The little man can't see outside of the box, and he can't feel the rushing air, so to him, it seems like he's peacefully floating inside of a box. Now, let's add a glass of water for him to drink. Look how the water slowly tips out of the glass and forms a wobbly ball. That's what water does when it has the chance to fall a long, long time with no air resistance. It forms into a wobbly ball. Now let's move our man and box further up before they hit the ground, say a couple hundred miles in the air, so they start falling again. There they go. But now we will give them a forward speed, moving faster and faster, so their forward speed matches the curve of the earth. This way, even though they are falling, they always stay the same distance from the curving earth. We call this constant falling orbit. We call the falling box a space station. And when we put men inside this falling box, we call them astronauts. This falling feels so much like what we imagine zero gravity to be that even astronauts and scientists often refer to it as zero gravity or floating or microgravity. But in reality, nobody has ever been in zero gravity. Astronauts have always either been falling toward the Earth or falling toward the moon. Understanding Newton's first law of motion will make you see the world a little bit differently. You begin to see things in motion as things that want to stay in motion. And the reason things stop or slow down is because forces interfere with them. Like on this carousel. Newton's law of motion, his law of lazy inertia, wants to fling me off in a straight line at right angles to the center of this ride. But the forces we talked about keep me here, getting pulled around in a circle. There are two other laws of motion Newton discovered, and we will look at those in our next segment.